Hi everybody, welcome back to Dave's Math channel. This is my continuing feature on the Math Lovers book, 3-volume series I wrote from 2019 to 2022. And I guess I might as well do another plug for it. This series is available on Amazon.com, both in paperback and Kindle. There's 3 volumes and these are pictures of them. And you can buy any of them or the whole set for I think that's I don't know. I think they're $40 a volume paperback, $20 a volume Kindle. I haven't checked the price lately, but I think they're a good buy. And just a little overview of what it is. Volume one, that's the one I've been going over for the last 5 months or so. This is more recreational math, um, and kind of advanced high school level, I'd say. Volume two is a little more academic. I go over topics like functions and calculus and probability and statistics. And volume three is problems and solutions. So these are problems pertaining to the first 2 volumes, as well as solutions to all the odd number problems. One other features in volume two, I have at the end of the book, I have 80 biographies, short bios of famous mathematicians throughout history listed chronologically, and I'm also doing a feature on them every Saturday. Gone through 17 out of 80 already. So that's a little overview of the Math Lovers book. I do encourage you guys to buy a copy, but if you don't want to spend the money, you can just watch my series. I will go over the first 2 volumes completely, I think. Anyway, today is my second video on permutations, and I didn't talk about the group theory yet connected with permutations, but there's actually something called permutation groups. So anyway, let's begin. So what is a permutation group? Well, I talked about permutations yesterday. Permutations are just a little brief review. You start with a finite set, and a permutation is really just sort of a way of rearranging the elements of the set. Um, so you can send any element to any other element, and there's a bijection. It's an automorphic bijection, meaning it's a function from the set to itself and it's one to one and onto, meaning that every element of S gets mapped by this bijection, and also every element gets mapped exactly once. So anyway, yeah, that's what a permutation is. And if you start with any collection of permutations of a finite set, those permutations will generate a group. And remember, a permutation we can write as a product of cycles. I talked about this last time. A product of disjoint cycles. And if you just had one cycle, the group you would get would be a cyclic permutation. So if you just had one generator, which was a single cycle, actually, if it's just one generator, you will get a group that's isomorphic to a cyclic group. But especially if it's a cycle, then I think it's pretty easy to see how it works. In general, you're going to get a more complicated group. Anyway, so I'm going to do some examples. This is kind of a mouthful. It's probably best to just look at some examples. So in the first example, suppose our set is S is just the numbers 1 through 4, 1, 2, 3, 4, and we're given three permutations. No, 2 permutations. P1 is the transposition. Remember, a permutation, a cycle of length 2 is what's called a transposition. So we have 2 transpositions here. P1 is the transposition 1, 2. This is the element that sends 1 to 2 and 2 to 1, but it leaves 3 and 4 alone. And similarly, P2 is the transposition 3, 4, which sends 3 to 4 and 4 to 3, but leaves 1 and 2 alone. So you might wonder if we put both of these transpositions into our group, what group does that generate? And it turns out the group that gets generated has exactly 4 elements. It's actually isomorphic to K4, the Klein 4 group. And the way to see that is you just see how all the elements act on the set, on 1 comma 2 comma 3 comma 4, and you have to keep the order intact. Um, and so I think you can see E. There's always the element E. That's the element that doesn't do anything. And if you act on 1, 2, 3, 4 with E, you get back what you started with 1, 2, 3, 4. But if you transpose 1 and 2, you're going to get 2, 1, 3, 4. So if you another way to say that is if you multiply your your ordered set 1, 2, 3, 4 by the transposition 1, 2, you get 2, 1, 3, 4. And if you act on it with 3, 4, you get 1, 2, 4, 3. I think these are pretty easy to see. The second one just transposes 1 and 2. Third one transposes 3 and 4. Or you can do them both. The fourth element in your set is the product of 1, 2, and 3, 4. And it doesn't matter which order you multiply. This is an abelian group. When you multiply both of these elements together, you can get both transpositions. So you get 2, 1, 4, 3. And I think it's pretty easy to see that this group you get is isomorphic to Klein 4 group because it has the same algebra. P1, that's the transposition 1, 2. Remember, every transposition has order 2 because if you do it twice, you get back the identity. So P1 squared and P2 squared are both equal to E. That's pretty obvious. And also, like I said, these two transpositions commute. And the reason they commute is because they're disjoint. They're disjoint transpositions. Disjoint past positions always commute. Doesn't matter the order. If they weren't disjoint, they wouldn't commute. But these two do. So we have P2, P1 equals P1, P2. And if you compare that with the algebra for K4, you would see that this group is isomorphic to K4. It's isomorphic to the Klein 4 group. So not a really exciting group, but it is an example of a permutation group. Pretty simple one. I'm going to do a little bit more complicated example now. Suppose our set now just has 3 elements. So now I'm using letters. I'm saying S is A, comma B, comma C. And now our generators are, our first one is, what am I calling P1 is A comma B. This is the element that transposes A and B. And P2 is the element, is the transposition BC. That's the one that transposes B and C. And these two transpositions do not commute. And the reason they don't is because they have a common element, namely B. So we have to calculate the algebra of this group. And it turns out that this is going to give you a group of order 6. That might surprise you a little bit. I mean, the previous example, we had 2 transpositions, each had order 2, and that generated a group of order 4. But this time we have 2 transpositions, also of order 2, and those two together actually generate a bigger group, a group of order 6. But the way we see that is we just have to do all the multiplications and see what we get. So if we multiplied, what is it? Um, yeah, so if we did, yeah, I think it's P1, P2, you'll find that you get the cycle ABC. I don't know if I want to do that in detail, but you can convince yourself of that. AB times BC equals ABC. Might as well do the work to show that. So remember P2. You're doing P2 first. When you write P1, P2, you always go from right to left. So P2 is gonna transpose B and C. That means you started with ABC, and now you're gonna get ACB. But now you're applying the P1, which is the transposition AB. So when you do that, now you're gonna get CAB. Is that right? Yeah, which is did I do that right? Uh, ABC. Um, Yeah, I think it is. So CAB, you'll notice that that's a cyclic permutation of ABC. So that's the same thing as if you multiplied by the 3 cycle ABC. So AB times BC is equal to ABC. And you can also convince yourself, I'm not going to do the work, but P2, P1, that gives you the 3 cycle ACB. So you get cycles of length 3 in both cases, but you get different ones. As a matter of fact, one's the inverse of the other one. Um, and and yeah, so P2, P1 is not equal to P1, P2. But now you can work out the algebra. I mean, you can just see how these things multiply together. I mean, I don't know if I want to do all the work here, but you can do this yourself and convince yourself that these are the 6 permutations of the set ABC. Um, and you can also show that this group has the same algebra as a dihedral group of order 3D3. Um, I think that's kind of easy to see actually, because P2, P1, that's ACB, that's the inverse of ABC. Um, I mean, ABC sends A to B, B to C, and C to A. ACB sends A to C, C to B, and B to A. You can see they're inverses of each other. If you multiply them together, you get the identity. Because one's going one way, the other one's going the other way. If you put A, B, and C, I didn't do this in this book, but if you wrote A, B, and C as a triangle, you would see that, at least geometrically, you would see that this group, it looks exactly like this. The group has the same action on this triangle as the dihedral group does on an equilateral triangle. So it is isomorphic to D3. So anyway, that's a second example. And these permutation groups, they're more abstract than geometric groups. Maybe that's why they're a little harder to visualize. But groups are really just defined by their algebra. So they don't have to have a geometric interpretation. They don't have to involve geometric symmetries. Remember, I said that group theory is kind of the mathematical theory of symmetry. Well, there are kind of abstract symmetries to this group, but they don't act unless you make it, unless you turn ABC into a triangle. They don't really represent geometric symmetries. They represent more abstract, permutations. Yeah. Anyway, so that completes my video for today. I hope I didn't confuse you guys too much. Anyway, thank you for watching. Long live math, and I'll see you guys next time.